So we'll move it a little bit to shallower crustal settings now, and working with 3D data, high resolution 3D, and scientific boreholes from IODP Expedition 396. And just starting here with an image from Kamchatka that shows sort of the active part of the systems you're looking at. So it's a nice fissure eruption here some decade ago, basically showing a large volume basalt flowing from the eruption fissure down on the slope, forming this sort of subaerial prolific type of basalt flows. You can also see in this picture is actually an ongoing eruption here at the volcano further to the north at the Klutchevskaya volcano. But, yeah. So outline of my talk, it's an introduction. I'm going to say a little bit about what SDRs are. Then focusing a bit on the seismic imaging and interpretation of SDRs. And then moving to some highlights from IODP Expedition 396. And just in the background here is another image just showing Fagradal shale eruption from last year, again, reminding us what type of systems we are looking at and working with. So as we saw from the previous presentation by Laura, that magma-rich passive margins are really common around the world. And of course, some of the more famous ones are in the Northeast Atlantic, in the Northwest Atlantic, in the South Atlantic, Western Indian margin, also around Australia and Antarctica. So this is a very common type of volcanic margins or rifted margins globally. And over the years, we've been mapping out in some great detail the distribution of breakup-related extrusive volcanic rocks, and we divide them into different seismic facies units. So the subaerial facies is what we call landward flows, inner SDRs and igneous complexes. The subaqueous facies is like outer SDRs, lava flows, and inner flows. And then we got these outer highs, separating commonly the inner and the outer SDRs. We also have igneous centers and the wide distribution of silt complexes in the sedimentary basins like the Børing Basin and the Møre Basin. And this was formed then during the breakup magmatism at about 62 to 54 million years. And these volcanic rifted margins are characterized by these thick sequences of SDRs up to 6 kilometers thick, and we also find them then onshore on the Blosseville coast of Greenland, or what we saw in the Disko, Nusvak, Svartenhuk area in the last talk. So why do you want to study this? Well, we want to determine the origin of large igneous provinces. We want to understand the birth of an ocean, and we want to unravel the impact on global warming and environment from this massive breakup magmatism. So this is sort of the overarching topics that we are working with. And to study this, we work on new interpretational methods. So we talk about seismic volcanostratigraphy and igneous seismic morphology. We acquire and develop new technologies for seismic data acquisition and imaging, using like 3D conventional, P-cable high resolution 3D and new processing flows. And there's a lot of improvements in the imaging of this setting over the past few decades. And we also then acquire new borehole data to calibrate our seismic interpretation. And I'll show results from the IODP Expedition 396. So what are SDRs? I worked on this since I started my PhD with Olav Eldon, and it was by sort of a coincidence working on some ODP Site 642. And in this paper, we went in seismic response and construction of seaward dipping wedges of flood basalts. So basically, it's definitely the S is for seaward. The D here is dipping. But then the R can have quite a few different meanings. And we talk sometimes it's reflector, so the actual physical interface, and it can be singular or plural. And we can also use it like reflection, so they're actually reflected waves. And it could also be singular and plural. And sometimes people also add S being sequences. So SDR sometimes is a terminology that it normally we end up using it as Siever dipping reflectors with or without the last S, basically. When it comes to the initial definition, like by Carl Hintz, data from the 70s, acquired of Norway, we see this very nice diverging SDR sequence here, and a well-defined base reflection that he called K reflection. So both the top and the base of the SDR is imaged here, but if you look at him, he called it wedges of very thick oceanward dipping layers beneath passive continental margins. But basically, John Mutter and colleagues at Lamont in New York and New Jersey, New York, they introduced this terminology of Siever dipping reflectors, and that's the most common usage basically of the SDR. So Siever dipping reflectors, physical interfaces. Yeah. Let's skip this. So what are these SDRs? Well, we can see from Iceland very thick, nice lava flows on here from the east coast near Reidafjordur. So it's they're composed of a large stack of lava flows, typically then placed subaerially, and this is our best type of analog for SDR sequences. But Iceland is also a fantastic natural laboratory where we can study actually the emplacement process of these large subaerial lava flows. And as you know, we have been going there quite a bit to study this. So this was prior to we went drilling. We flew over Reykjanes, and here you can see the Fagradalsfjall eruption. So the eruption site is up here. The lava is following down slope and then ponding into any type of structural low. It's important though to remind yourself that Iceland is quite a different setting that we have on most margins, because you have all of these subglacial hyaloclastite ridges. So the topography is much more pronounced here than you find on most rifted margins, and therefore also the development of SDR sequences is different on volcanic rifted margins than on other places. And also in Iceland here, where we have this current eruptive phase, you have an enantiolong sort of rift system. You go to the current one, eruption phase that's been happening over the last month. We basically see at Grindavik that none of this magma that is moving in the crust never reached the surface, and it's quite typical in this area that is fairly magma-starved system. So we have intrusive magmatism, but not a large component of extrusive magma, although it might happen at any type of the future. This is a picture here that I took with Morgan up in a few years ago, showing basically the active rifting system, fissure system here, where we have previous historic eruptions. But again, we see the last lava flow is flowing down slopes and depositing at these large lobes. So this is both the active and the remains of these fairly large basaltic volcanic complexes. So this is a seismic image showing some of these lava deposits on the mid-Norwegian margin. And we can see that this is a top basalt horizon up here. It's a large escarpment, and we find a lot of reflections below the top basalt. So it's actually quite a lot of great imaging, seismic imaging of these breakup volcanic complexes, but we really need to develop, and we are developing new interpretational methods. And it started basically developed the concept of seismic volcanostratigraphy on 2D data. Then we pick sill intrusions on with characteristic saucer-shaped geometries. And then we look at igneous seismic geomorphology on surfaces in 3D. And of course, well ties and field analogs are really important to give a geological interpretation of these seismic facies units.
We're now at 10 minutes, okay?
Yep. So this is an example here where we see the SDR sequence, again on the varying margin, on a bit more modern data. So we have the SDR sequence, divergent patterns, like swarms, most likely fishery systems, high velocity, lower crustal body, and we have the drilling of the ODP 642. Another similar type of profile on the varying margin, where we have an SDR sequence, we have an outer high, we got the escarpment, and basically this wedge-shaped unit with divergence reflection and several subsequences is what we call the inner SDR. So it's formed during the early breakup phase with lava depositing in a rift basin. And these are two proposed drilling sites that we made. On 3D data, we can really interpret or understand the nature of this lava flow field. So this is a top basalt surface on a 3D on a varying margin, where consists of a horizon peaking, and then we do RMS amplitude extraction and do a color blending. And you can really see that individual lava flows are flowing from the west towards the east, coming out in these lobe-shaped geometries and come to the paleo coastline. They will fragment and they are transported down this kilometer-high escarpment and being deposited in the nearby graben as volcaniclastic deposits. Just another example here. This is from the top basalt surface. Again, when we do the seismic geomorphology, we can go from a bit uncertain reflection into defining really nice lava flow margins and graben structures and even like compressional ridges on these type of data. Finally, with 3D data, we also have the advantage that we can look at the geometries of these reflections in 3 dimensions, and ODP 642 drilled then about a kilometer of lavas here that we calibrate with the seismic reflection data. It's worth to note that we have much more, about 10 times as many flows as we have reflections in these areas. So individual reflections are interference phenomena and not reflections from boundaries between lava flows. Now jump to the IODP Expedition 396. So in 2021, we went out into the Norwegian Sea from Reykjavik, drilling basically at 10 sites, at 10 different holes. And the majority of these targeted then the breakup volcanic complex. So at least at the Kolga site, at the Skål site, out at the Eldø High and in the Lofoten Basin. And I'll show you some of this. It was very highly successful operations here, more than 4 kilometers. We drilled 2 kilometers cord, and we recovered something like 356 meters of basalt and 15 meters of granite quartz. Fantastic core material. So what's most relevant to this talk is what we drilled of the basalt terrain. So we drilled 1 sub-basalt borehole here at Kolga. We drilled 2 sites here on the different sequences of the SDRs. We drilled an outer high and an outer SDR. I think it's the first time people drilled outer SDRs, as I know. So in addition to having these type of large 3D cubes, we've also been acquiring high-resolution 2D and 3D data with the University of Tromsø, and I will show some of that at AGU next week. Just the first site, an enigmatic structural high. Basically, we have here interpreted the top and the base basalts. Nice SDRs in the west, a basalt window on the western part of this Kolga high, and then prograding lava delta reflections and sill intrusions below. When we went in and drilled this enigmatic place, we actually discovered granites, and people were a bit surprised. Some people thought it could be some loose blocks, but then we went and drilled the feather edge of this SDR sequence, drilling through something a bit more than 100 meters of Siberian basalts with granitic sandstone in between, and then about 30 meters into the granite again. So clearly this is a large granitic intrusion, and it's most likely just Paleocene in age, so related to the same igneous system. We go to the Skull High. Here we have the SDR sequences, the base basalts. But if you look at the geomorphology here, we see that it's two very different areas, that we have this very pitted surface in the west, whereas we have a faulted surface along this structural high. The covered material, we find a lot of vesicular basalt, open vesicles, and interbedded volcanic clastic sediments, quite thick in some places. And some of these basalts really have very high permeability. It's just a video Peter Bethlehem made almost for fun on the cruise, and John, and just seeing that the permeability is very locally very high in some of these 56 million year old of 55 million year old lava flows.
You're now at 16 minutes.
So I will round off quite quickly, just showing what we drilled at the flank of the Eldjö, this outer high. It was named after Olav Eldom that died in March 22. So here we drilled into one of these high amplitude reflections, recovering pillow basalts and hyaloclastites. So clearly some sort of subaqueous magmatism, whereas we drilled the outer SDR sequence. It's not as well defined as the inner SDRs, but again, we find a lot of basalts here in this site and thick intrabed volcanogenic and biogenic sedimentary rocks. Just my summary. It's partly based on Olav's sort of vision or interpretation of a volcanic rift at margin. Some of the scientific challenges we're working on is really how the volcanic margin works, and the premises here goes on. They're part of a tectomagmatic system. The plate tectonic framework should be established, and then we link it towards the global implications, how the Earth interior works in terms of mantle plumes or other type of melting processes, and how the magmatism and volcanism influence the world's exterior and environment. So just say here, we are well into the scientific studies after the drilling campaign, but there's quite a bit of remaining work going on. But we have drilled 20 holes at 10 different sites, and some of the main research that we're doing is related then to understanding the breakup magmatism, the Paleocene-Eocene thermal maximum, and the development of ocean. Some initial results from some of the sites drilling the hydrothermal vent complexes was recently published. And then just need to say thank you to the crew and the scientific staff participating on this leg. It was really a fantastic platform to work from, and it's great when everything works as it did during this expedition. Just finally mention that all of the results, the proceedings have been published, and both the proceedings and the data are available on the IODP websites. Thank you.
Thank you very much, Sverre. Absolutely amazing, beautiful seismic data and interesting drilling results. Does anybody have any question quick? We are pressed a wee bit for time. I do have one remnant question from Derek, who did have to run away. And his question is, in your high resolution seismic data, can you see and map the bounding faults at the foot of the SDRs? Or are the Norwegian versions just magmatic?
So one of the problems on the Norwegian margin, we have a fantastic data coverage until where the exploration license blocks have been defined, and that's sort of in the middle of the SDRs. And the coverage from the middle part out into the oceanic part, it's much more limited. Then we have to go by mainly 2D data. So in that way, we cannot map faults at the termination of the SDRs, as we only have the conventional type of 2D data.
That's fair. So were all of the drill sites, I guess all the inner ones had 3D coverage, but then the outer ones had 2D coverage for deciding on the drilling locations?
Yeah, so the two outer sites had only had 2D 2D coverage. The rest of them had 3D.
Okay.